This demonstration video will guide you through computing the flow around a commercial aircraft at different flight altitudes, Mach, and engine regimes, and analyzing your results using parametric plots. The aircraft considered is a NASA Common Research Model in the wing, body, nacelle pylon configuration. The flight conditions used in this tutorial represent examples of climb and cruise conditions and are for demonstration purposes only. The workspace is available within the Fluent launcher. Begin by selecting Enterprise under the capability level and an arrow from the list of workspaces. Set the number of solver processes to 8. Click Start to open the workspace. Create a project by selecting New under the project ribbon. Name your project Fluent Aero Demonstration. Create a simulation by selecting New Aero Workflow and select your input grid. In the new simulation window, name your simulation as shown and enable Load in Solver. The case file will now open and a background solver session will be loaded. A new simulation folder now appears under the project view. Your input grid is now imported as CRM WB-NP aircraft.cas.h5. Head to the Geometric Properties panel and define the orientation of the geometry within the computational domain. This is used to compute aerodynamic forces. Set your conditions as shown on the screen. After defining your geometric properties setting, enable Compute Projected Area. In the Projected Surface dialog, set the following settings and select all areas beginning with Wing-Main. Press Compute to compute and display the reference area. Lastly, press the Use as Ref Area button to use the computed area as the value found under the Reference Area box in the Geometric Properties panel. In the Airflow Physics panel, set your solver, models, and material exactly as shown here. In the Simulation Conditions panel, you will now set up the free-stream flight conditions. 3 Mach numbers will be used. The first 2 represent climb conditions, and the third is representative of typical cruise conditions. In the Flow Speed section, select Uniform under Distribution and set minimum Mach number and maximum Mach number to 0.3 and 0.7 respectively. Set the number of points to 3. A column for Mach number will be created and populated in the Input Design Points table. You will define 4 angles of attack for each Mach number. Under the Flow Direction section, set the distribution to uniform to set the angle of attack for each design point. Set the remaining settings as shown on the screen. 12 design points have now been created. You have 3 Mach numbers and each flow speed has been associated with 4 angles of attack. Under the Pressure and Temperature section, set the parameter to altitude and the distribution to custom. A column will appear allowing you to specify the altitude per design point. Set the altitude for each Mach number as shown here. The pressure and temperature columns will be automatically computed from the International Standard Atmosphere model at the altitude of each design point. You will now create several aircraft components, allowing you to define some component-specific inputs and outputs. In the Setup tree, go to the Component Groups. In the Properties Component Groups window, click Manage Components. The Component Manager panel will appear. Begin by creating an engine type using the default group name that appears. Next, use Create to add engine_1 into existing components. All boundary conditions not assigned to a group are listed under Available Zones. An engine type group is a specific type of group which contains 3 component parts such as exhaust, intake, and nacelle. At least 1 boundary zone must be added to the exhaust and intake component parts. From Available Zones, select Engine Inlet and use the Add button to add it to the intake component part. Select and add engine nozzle to the exhaust part. Select and add all the remaining boundary zones starting with engine to the nacelle part. The Engine 01 component group is now successfully created. Follow the same steps mentioned previously for the wing component. Modify type to wing. Use Create to add wing_01 to the existing components. From Available Zones, select all the boundary zones that start with wing and use Add to add them to the wall's component parts. Once again, follow the same steps mentioned previously for the fuselage component. Modify type to General. Use Create to add fuselage_01 to the existing components. From available zones, select all the boundary zones that start with fuselage and use Add to add them to the All Component Parts. Click OK to close this dialog. The newly created components now appear in the outline view, in addition to the default free stream and other groups. Expand Engine 01 and select Engine Inlet, which is a pressure outlet type boundary zone. Type in exactly what you see in the Engine Inlet Properties panel. You are setting static pressure to custom to apply different static pressures for each design point. A custom expression for static pressure is created in the solution workspace and is named inlet_P. A column with that name also gets added to the input design points table. You will enter the values of inlet_P in a later step. Highlight Engine Nozzle to set the boundary conditions at the engine exhaust. Select and type in exactly what you see in the Engine Nozzle Properties panel. You are setting static pressure, total temperature, and mass flow rate to custom in order to apply different static pressure, total temperature, and mass flow for each design point. Fill in the input design point table with the values shown here. In the Properties Component Groups window, click the Manage Outputs button to enable component-specific output parameters. From the Manage Component Output panel, check the active box of the Freestream, Fuselage, Wing 01, and Engine 01 components. Check the Monitor box of the Wing 01 component. Since active is enabled, the mass flow balance of the Freestream group, the lift and drag forces of the fuselage, and Wing 01 components, as well as the thrust and mass flow balance of Engine 01 will be calculated and summarized in Component Outputs table when the calculation terminates. Since Monitor is enabled, the evolution of the Wing 01 lift and drag outputs will be plotted in the convergence plot. Notice that there are 12 design points and 11 columns in the table. The first two Mach numbers correspond to climb conditions, and the third represents typical cruise speed conditions. For each Mach number, you simulate 4 angles of attack using the same flight altitude and engine conditions. Head to Solve and specify 1000 iterations and default for convergence settings. Press Update to launch the calculation. When the calculation begins, design point 1 will be simulated. A convergence window appears in the graphics window area. It will display the residuals and monitors of design point 1. Design point 1 will run until the total number of iterations or convergence cutoff have been satisfied, whichever comes first. The remaining design points will follow the same cutoff criteria. This concludes part 1 of the video series. In part 2, you will verify the convergence of your calculation and post-process your results in Fluent Aero.